Well, today we do the second exam for Level 3 Physics. This is Understanding Wave Systems. I think this is the least examined physics exam that's used. For all of these exams, I'm going to be using the formula sheet, which is provided, as well as the standard Casio calculator. I'm going to presume as well that you don't need me to explain to you what a wave is, that you know the basic physics and you just need help with the problems. Okay, with that said, let's do it to it. All right, so the first question is the Doppler effect. Martin and Kieran are riding their jet skis on a lake. Why do they give these people names? Why can't they just say there's a jet ski on a lake? Martin, his name's changed. Martin. Okay. Martin with an I and Martin with a Y, we're presuming they're the same person. Jet ski is fitted with an air horn. Oh, that guy. Emits a frequency of 1043 hertz. At one point, Kieran, also with a Y, and Martin with a Y, travels directly towards her at a speed of 27.3 meters per second. The speed of sound in air is given here as 343 meters per second. Calculate the frequency of the sound that Kieran hears. So for this, we're going to use the Doppler equation. So the Doppler equation is, let's explain it. So F dash is the observed frequency, which is the one that we're looking for. This is the velocity of things through a wave, the wave through the medium, and this is the velocity of the source. So we don't know what this one is, and it's going to be in hertz. First thing we need to check, are these in SI units? Yes, they are. 1043 hertz, that's SI units, and 27.3 meters per second, that's SI units, and that's also in SI units. So F dash is going to be equal to 1043 times velocity through air is 343 over 343. Now, is it going to be adding or subtracting? And it's going to be subtracting. The way I remember it, we take away if the distance is decreasing. If the distance between is decreasing, we use a negative. We use a positive. You see up here in the formula, it's a plus minus. We use a positive if the distance is increasing, i.e. they're getting further apart. So it's going to be minus whatever this is, and it's going to be minus 27.3. Close brackets, and it's all in one bracket, so we can use our calculator now to solve it. So let's just get out of there. Let's do the bit in the bracket first. Minus 27.3. Close brackets, and we get that, and we want to multiply that by 1043, and we should get 1133.2. So it's going to be higher in pitch. Okay. Next question says, explain why Kieran with a Y hears a different frequency from that emitted by the jet ski's air horn. Well, if we have this idiot with his horn here, it's going to propagate in all directions. And the sound waves, as it's moving in the direction that the sound is moving, are going to become compressed. So the wavelengths are going to go down and they're going to shorten. And because the wavelength goes down, the frequency will go up. So the number of wavelengths going past Kieran's ears increases. So I'll just bring up a simulation so you can see how that works. Okay, so here is a simulation on O Physics. I'll leave the link in the description. So here's the source. So this is our charming fellow on a jet ski with a blowhorn, and this is the poor person just trying to have a nice walk by the lake. The source frequency is what's going to be coming out of this source. The perceived frequency, because it's going to be moving towards them, it's going to be compressed. So the source wavelength, they're coming out at 1 meter intervals, but the wavelength when they hit the observer is at 0.75 of a meter. So they're going to hear it at a higher pitch. So I'll just start it. So you can see here, as it's moving in the same direction as these waves, these wave fronts are being compressed in front of the source, and then they'll cross, and now they're moving further away. So they're now spreading out, so it's going to appear to be a lower frequency. So I'll reset it and play it again. See, here's the source. It's sort of catching up with the sound waves. And as it gets to the observer, notice that the frequency swaps, because now it becomes a plus sign, so now it's going to be a lower frequency. Alright, now we're told that Karen is floating very close to the path of Martin with a wise jet ski, while her friend Erin with an eye is watching from a bank on the edge of the lake. So this hooligan Martin here is tearing along on a straight line. Here is Kieran with a Y, here is Erin with an I. So the graph shows the frequency of sound heard by Kieran and Erin as the jet ski travels from A to C. So the jet ski is going to move from A to C. Kieran is going to hear pretty much the same tone, and then all of a sudden it's going to drop and then go down to the same length as Erin, and Erin will hear the tone gradually dropping. Here they'll hear it at the same time, and then they'll level off there. And it's basically saying, explain why the frequency that Kieran hears is the same or different to that which Erin hears. So it all has to do with this little variable here. So the frequency that the jet ski is emitting doesn't change. So F, the change in F is 0. The velocity of the sound through air is going to be the same. So the change in VW is also 0. However, Vs is the relative velocity. Okay. How quickly something is moving with respect to something else. Now, the velocity is distance over time. This distance from here, where, do this, the highlighter, the distance here from Martin's jet ski to Kieran is a straight line. So the sound that she hears is going to be the same as long as he keeps the same velocity himself. It's going to compress the waves an equal amount the whole time until it reaches her, and then the plus sign becomes a negative sign. So this plus sign here will become a negative sign, here will become a plus. So that is why there is the sudden drop when you're close. Erin's distance is a bit different. Velocity is distance over time. Here is the distance that we're measuring for Martin. So when Martin moves from here to here, the change between Martin and Kieran here, that change is a lot less than that change. So he's covered effectively more distance towards Kieran in that time than Erin. That's why there's a different tone in it, and it's a gradual tone. This is, of course, it's a right angle triangle. And you can think, well, that's a terrible triangle, even by my standards. And you can think of the line between Martin and Aaron as the hypotenuse of the right angle triangle. And this triangle, so this would be what the adjacent side is going to decrease at a slower rate than the hypotenuse. And in fact, this one is going to remain the same because the wavelengths are going to be uniform. As long as he's going in the same direction towards her, it's going to have the same tone. Whereas here it's going to be a sine wave, so it's going to kind of drop in a more sort of wave of a wave like function. Okay, so that's how you would explain it. VS is variable, and that's what changes. And then I guess we could say that when it passes, the plus becomes a negative. So before it was plus velocity of the source, and after it's gone by, it's negative the velocity of the source. So now in part D, we find out that an underwater microphone has been submerged in the lake by Big Brother to monitor noise pollution from jet ski engines. About time. Martin with a Y jet ski engine makes a sound at 574 hertz. As the jet ski travels away from, okay, so it's away from, so we're going to need to use the plus. The underwater microphone at 27.3 meters per second. The microphone measures a frequency of 563.6 hertz coming from the jet ski engine. Calculate the velocity of sound in water. Okay, so they just dump you with a whole bunch of information and you have to sort of pick out how we solve this. So again, we're going to use the Doppler equation here. And the trick here is we're going to make it become an algebra question as quickly as possible. So F dash is known, it's at 563.6 hertz. And we know that the F actual coming off this thing is 574 exactly. And we know that the velocity of the source here is 27.3 meters per second. We don't know what the velocity of the wave is in water. Just a heads up, it will be greater. Waves tend to travel faster in water than through air, including sound. Sound travels a lot faster through water than through air. Now, we'll do the algebra and then we'll put the numbers in. So we want to solve it for VW. So F dash equals F VW, and it's moving away from that there. So how are we going to do this? So let's divide both sides by F. So F dash over F, and that's going to be equal to VW over VW plus VS. Now it's going to be a little bit trickier, so I'm just trying to think this was a really quick and nasty way of solving this. I guess we'll just cross multiply it. So F dash VW plus VS minus F times VW equals 0. So F dash VW plus F dash Vs minus F times Vw equals 0, and now we can factor out that Vw. Okay, so we're almost there. So Vw is going to be equal to minus. Okay, so now we have all of the numbers that we want, and we can put in those numbers now and solve it. Okay, so we've got, let's do the top. So minus, what did I say? 5. So minus 563.6 times 27 point, what's speed? 27.3 is that. So we're going to divide it by 563.6 minus 574, and we get 1479.45, and we have to have that in meters per second. So the trick there was to turn it into an algebra question as quickly as possible. Maybe I kind of fluffed up a little bit of the algebra there, but as long as you stick to the rules of algebra, we want to solve it for VW. So we're up to question 2, standing waves. So a cello is a string instrument belonging to the violin family. Okay, the strings are supported at each end by a piece of wood called the bridge and the nut respectively. And here's a picture of a cello that's been mostly blacked out except for the spike down the bottom. They forgot to edit that bit out. Why you need to redact a picture of a cello is beyond me, but okay. When the cello is played, the strings can vibrate in different harmonics. Draw a diagram of the fourth harmonic, label the nodes and the antinodes. Okay. So if it's the fourth harmonic, the wavelength is going to be the length of the string divided by 2. Bit of an autistic 2 there. Okay. So there are 1, 2, 3, 4, 5, 6, 7, 8 squares across. So each square is going to cycle twice. So it's going to go, you're going to have to excuse my terrible art skills. Okay, so that's where it's going to be. So it's going to go up like that, and it's going to come down here, and then it's going to level off, and then go at half the wavelength, the half of the length of the string, and then it's going to kind of level off there and come back again. So that's the actual wave. Here is the sort of what it would be, its maximum extent. I'm going to draw that just dotted. So that's where it's going to be when that's the maximum displacement on the other side. So the main string there is the blue bits. So the nodes, one there, one there, one there, one there, and one there. The nodes are the bits where it doesn't actually move. This is an antinode here, antinode here, antinode, antinode, and we're just ignoring the dotted bit. That's how we do the fourth harmonic. Way to remember it is if we draw the shadow string, it's going to have 4 humps. The way to remember that it's the fourth harmonic. The next one is quite an interesting question. Sometimes if the cello has been in storage, the tension in the strings will decrease. So think of it, things that have been stretched after a while, they're going to sort of stay stretched. And the instrument will be out of tune. The strings will therefore play a frequency that is other than the desired frequency. So your common sense should tell you that if the tension goes, and it's going to drop in tones, but we'll see what we get. Use the equation below to explain how this could have caused the frequency to be higher or lower than the desired frequency. Okay, well, if, let's say that, let's use mass per unit, the change in mass over time is going to be 0. This thing isn't going to gain or lose mass. The strings aren't going to gain or lose mass. Okay. The tension on the strings will decrease. So change in tension over change in time is a negative number, is going down. So therefore, tension over mass must be going down, which means that the square root of that must also be going down, which means that the velocity of the wave on the string must also be going down. Okay, so tension goes down, and that means that the velocity on the string goes down. Now, velocity on the string is going to be equal to the frequency times the wavelength. Now, the wavelength that we want is not going to change. An A note is going to be an A note. It's going to be an A note. So it's going to stay the same. But V wants to go down. This can't do anything. So this must go down as a result of that. Mathematically, that's the equation. The string gets less and less able to vibrate quickly, therefore the frequency must drop. So anyway, you wanted to explain that in words, that'll be fine. This next one is a little bit of a tricky one, and it's one where you really do need to know a formula which is not given to you. So we're going to use this one here, but the wavelength for a harmonic, so this wavelength of the harmonic is 2 times the length of the standing wave, the medium, over the number of the harmonic. So if the harmonic is 1, then the wavelength is going to be 2L, because 2L over 1 is 1. Okay. Given that, we can use this one now. So the velocity is given as the frequencies. Let's call it frequency 1 of the first note, which is 147 hertz, times 2 times the length of that string. But notice the velocity is going to stay the same. So the frequency of the second note times 2 times the length of that second string is given. Okay, so how I got that one first by knowing this formula. This is the key formula. In fact, if you're going to remember any sort of formula that they don't give you, it'll be that one, the wavelength of a harmonic. So we can eliminate the velocity. The velocity of the sound is going to be exactly the same, or the velocity of the string is going to be exactly the same. Now we can put in those numbers. So F1 is 147 hertz. So when a 0.690 meter string is played on the first harmonic, 147 hertz, then staying on the first harmonic, so it's going to be N is going to equal 1, and F2 is going to be 207. So length 1 is 0.690 meters, and that's going to be equal to the frequency of the second harmonic, which is the second note, sorry, and that is at 207 hertz, times length of 2, and we don't know what 2 is, so we have to find it. Let's move this up. So length 2, if we do the algebra, is going to be 147 times 0.690 divided by 207. It's 07, isn't it? Yes, 07. I couldn't read my own mind writing. And now we get out Mr. Calculator. Mr. Casio comes to the rescue. So 147 times 0.69 divided by 207 is 0.49. So 0.49, which is the same as 49 centimeters. Same harmonic, higher note. Okay, so let's move on to question D. So two strings that are next to each other in the cello are played at the same time. When string 2 is played without a finger being pressed on it, so it's an open string, it produces a note with a frequency of 98 hertz. So 98 hertz. So our frequency that we're starting with is 98 hertz. So strings 1 and 2 are played at the same time that a finger is pressed into string 1, so the big string at the bottom end there, and the length of string 1 is gradually reduced, so it goes up in tone, so the frequency will go up until a beat is heard. So it doesn't ask you to work out what the frequency would need to be, but it asks you to explain why beats form. And it has to do with constructive and destructive interference. So when you make a note, two notes when they combine, so this is like one note, and this is another note which is kind of on a different frequency. When they are added to each other, they will produce like this sort of bigger note. Where they interfere with each other, it will be a node, and where they construct or destruct with each other, it will be an antinode. And that difference is the beat. So if you have one beat which is, say, well, let's use the one they've got here, 98 hertz, so it's going to be like kind of sound, and then you have a beat which is 1 or 2 below a multiple integer values above or below that, the frequency of the beat is going to be the absolute value of first frequency minus the second frequency. So the difference in the beat. So if this one here is frequency here, let's say this is our 98 hertz wave, and this one here is our 100 hertz, say for the sake of argument, you won't hear kind of two notes distinctly, but you will kind of hear one note going at two beats per second. So you won't hear like rrr and rrr at the same time. I think that sounds terrible, but you will hear kind of like wop 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 wop. I'm not gonna play that. I'll put a link to some software that will let you play those. The reason I'm not going to have it is because it would probably sound really, really unpleasant. It is a really, really unpleasant thing if you're not used to it. So just note that the two, when they're added together, they make sort of one super note. So maybe here's an illustration. So this is one wave which has a wavelength of 1. So whatever 1 is. And this one has a wavelength of 2. So when they're combined, when we have them on top of each other, like that, they're going to form this kind of peak here, which is going to be at a frequency of 1 because the difference is 1. If I change this to say 4, it's going to have a frequency of 3. So this thing here is going to be every third beat, it's going to move sort of that sort of frequency. So when you add them together, you have like this sort of super wave that is both of those waves combined. I can't think of another way of explaining it, but other than playing one. You would have heard it if you listen to rock music, when you have sort of a bass playing two open strings. Quite often the harmonics will interact with each other, and you'll get this kind of like whirring sound, kind of wah 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 sound. Pink Floyd uses it quite a lot. Okay, so I did know this next one was coming up. I kind of explained this one. So explain what will be heard as the length of string continues to be gradually reduced. Well, if the string is reduced, then the frequency will go up. So the absolute value of frequency 1 minus frequency of 2 is also going to go up. So therefore you're going to get more beats. So let's say that the first frequency, for the sake of argument, is 98 hertz, and frequency 2, instead of, let's say it was started at 99 hertz. So the beat, you're going to get 1 beat per second. So it's going to be kind of a whoop, 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 whoop. If we increase the frequency of the second string here, so F1 is still 98 hertz, but F2 is now 100 hertz. So the difference now is 2 beats per second. So now it's going to be like whoop, 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 whoop. And again, if we increase it again, say 105, you're going to get this kind of whoop, 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 whoop. And then eventually the beat frequency is going to be so close together that you're not going to hear it as a beat. You're going to hear it as sort of one very loud tone. It's going to be, whenever you set up audio equipment, you really want to avoid that because it is really, really unpleasant. A high volume beat is really, really nasty. It's kind of one of the reasons why you can hear these big boombox cars coming from miles away, because not because necessarily that it's loud, it's that it's the frequencies are just, any difference in the frequency is just going to be amplified. It's going to be, it's going to be good for the person in the car until they go deaf, but really unpleasant if you're trying to sleep. All right, so we're up to question 3. We're on the home straight. So question 3 says that a laser shines green light onto a double slit. So we're going to be replicating in a way the Heisenberg double slit experiment that you would have, if not done in class, then you would have definitely had it explained to you in class. I'm not going to go into the physics of why it splits, superposition, and light being a particle in a way. I'm not going to get in there. We're just going to answer the question. You've got pretty much just an hour to do this exam. Don't try to explain quantum physics. Just give them the answer. So the slit separation of 1.25 times 10 to the negative 4. So it's in meters. So let's kind of underline that. So that's going to be something. Each slit then acts as a light source that is in phase, which is good to know, producing an interference pattern on the screen with fringes that are close together. Okay. The screen is 3.40 meters from the slits. The distance from the central maxima to the third order maxima is 4.20. I think NZQA having a joke there, times 10 to the negative 2 meters. Show that the laser has a wavelength of 515 nanometers. So 1 nanometer is 1.0 times 10 to the negative 9 meters. It's 1/1000th of a meter. Pretty small. Okay, so it looks intimidating. There's all sorts of variables being thrown at you here, but this is really just an algebra question and knowing which formula to use. So let's explain it. So it's going to be this famous one here. Just trying to remember from memory how they want it presented. It's done in different ways. I really hate this dx here because it looks like you're doing calculus. It looks like you're taking the derivative of x, but you're not. It's d is a measurement, x is a measurement, l is a measurement, and they're all in meters, so you need to know which one is which. Okay, let's explain these things. So, what are we looking for? We're looking for the wavelength. So the wavelength, we don't know it, and we're going to see that it's 515 nanometers. So I suspect that that's there because if you get like a really crazy answer, you'll know that you're way off. So this is going to be lambda. So this is the wavelength of the laser itself. Okay, n. N is the kind of, think of it as the sort of an index number. And it's the distance from the central maxima on the interference pattern. So let's kind of explain these numbers. So on the back screen, we have this pattern. So here is going to be the main maxima. Then there's going to be sort of dots going off here to the side. And they're in phase, so it's going to be nice and symmetrical for us. We don't need to worry about this being distorted. Okay, this is the central one, so this has an n number of 0. It's kind of ground zero. This is n1, n2, n3, and two ways of doing this. You can use negative numbers, but I just say it's just 1, 2, 3. So these are whole integer numbers, and the n, think of it as the distance. So the distance from here to here is 1. And they want the third one, so it's the distance from here to here. So that's going to be n equals 3. Okay, so this is the third one, the index number. All right. D. So D is the separation of the slits. So here we have our laser that we're firing, and these are going to be two. They're going to be obviously a bit further apart than that, but this is going to be D. So this is going to be how far apart these things are. And that's given to us as, what is it, 1.25 something? 1.25 times 10 to the negative 4 meters. Okay, this is equal to 3. Okay, x. X is the distance from the maxima point to the third one. So x is the distance from this point here to this point here. So this is going to be x. So this is given as, what do they say? 4.2 times 10 to the negative 2 meters. Nearly there. L is the distance from the slits to the screen. So it's going to be this distance from here to the screen. This is going to be L. So the laser is going to hit there and going to sort of interfere with each other and form these patterns. The distance between the screen and the slits, not the screen and the light source, the screen and the slits, is going to be this L number. Okay, so what are we trying to solve for? We're trying to solve for lambda here. So we need to bring this n over. So we need to do a little bit of algebra first. So let's copy this formula down. So we're given n, oh, that was funky, n lambda equals dx over big L. We want to make lambda the subject, so we're going to cross multiply it. So lambda is going to be dx over L times n. And now we've got everything that we need to solve it. So this is going to be 1.25 times 10 to the negative 4 times x is 4.20 times 10 to the negative 2, and they're in SI units, so we don't need to put the m, divided by L, and L is given to us as just 3.4 meters. 3.4 times, and the index number is 3. And we have enough now to know what we're going to get. So we're going to grab Mr. Cassio and he's going to help us solve it. All right. So let's do the top first. 1.25 times 10 to the negative 4 times 4.2 times 10 to the negative 2 divided by 3.4 times 3 in brackets exe. What do we get? We get 5.147 times 10 to the negative 7. Okay, but we want it in nanometers, so we're going to need to move this 2 places to the right, which is 514.7 times 10 to the negative 9. And we wanted to test that this is equal to 515. So yeah, it is. So this is equal to 515 nanometers if we're doing 3 significant figures, which is what's advised. Okay, so a lot of information there. The big thing that you needed to know was which formula to use and what the variables actually mean. If you know that, it's just an algebra question, but if you didn't know that, you'd be best just to skip over this question. So on to question B. Explain why the intensity of light in the screen varies as shown. And the answer to this, as a lot of things, is constructive and destructive interference. So when the light goes through the slits, it's in a superposition and interferes with the wavelengths, because both the slits are a light source. So it's actually get a simulation so you can see what's going on. Okay, so here's a simulation from Physics. Again, I'll put the link up in the description. So here we have the 2 slits, so let's take those off. So here is our separation. So this is the D, the distance between the 2 slits. This is L here, so this is the distance from the slits to the screen, and if you can read that, it's in 10 micrometers. So obviously it's not anywhere near the scale that we have, but the light source is going to come through these 2 openings here, and these are going to act as light sources. So let's fire the laser off, and it's going to hit, and it's going to interfere. So you'll see these sort of bands here, the nodes and the antinodes, as they move out and interfere with each other. So let's have those. Let's remove the wave fronts. So this is a sort of a loci of points of the maxima. So where this hits the screen here, there's going to be a bright spot here, a bright spot here. This is going to be the central bright spot, bright spot, bright spot. There's only room for 2 either side on this one, because if we make it too small, it's going to be weird. It's going to look weird, and you're going to have this funky whatever's going on here. So here's the interference pattern that it's going to make, and it's going to be not very useful. let's change the pattern. So here's a bit nicer color. So we have the wavefronts, we introduce them here. So maxima, 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 maxima. So we predict there's going to be a bright spot there, a bright spot here. In the middle here, there's going to be one here and here. So let's make the interference pattern. So notice these bands that are forming here over time. Okay, so here's the central band here. This is going to be n equals 0, n equals 1, n equals 2. And this is n equals 1, n equals 2. So here where the maxima meets the maxima and there's constructive interference, it's going to be really, really bright. Here in the middle, where they are destructively interfering with each other, it's going to be not very bright. So if we go back to our screen here, this represents a maxima interference, maxima, central node, first, second node. Well, n equals 1, n equals 2, n equals 0 here. Okay, do I need to write anything? Yeah, I think that's all they really want. I mean, you could say that the wavelength is going to be at 0, 1 lambda, 2 lambda, 3 lambda. So that's going to be the bright spots. And the dull spots, where there's destruct, the antinodes, is going to be lambda over 2. Yeah, 3 lambda over 2. This is from memory. 135 lambda over 2, 7 lambda over 2. So this is going to be dull spot, dull spot, dull spot, bright spot, bright spot, bright spot. So why does the intensity fall off? Well, it's just diffracting more. If we go back to our simulation, it's diffracted a lot more, so that there's a lot further distance that it has to go to interact. So the intensity of these waves out here is going to be less intense. Maybe that's an unsatisfying answer, but it's going to sort of die away as the intensity, as one dominates over the other, the interference is going to be less pronounced. I think that's a good enough explanation for year 13. It really is a university year 1 thing here. If quantum physics will do your head in, and I don't want you to do your head in. So now the double slit is replaced by a diffraction grating. So think of this as a sort of a piece of glass with lots and lots and lots of grating, diffracting slits on it. They're closely spaced slits. Describe and explain the changes to the interference pattern observed on the screen. So for this one, there is a sort of a paradox at work. So because the formula is d sine theta n lambda, the distance between the bright spots is dependent on this angle. So let's actually do a quick little simulation actually. So here is another O physics. I'll put the link in the description. So here we have the laser, and as it's hitting the diffraction grating here, it's splitting into lots and lots of interference patterns. So there is the paradox that as the number increases, so the distance between them decreases, they get further and further apart. So it's a Heisenberg's paradox, and we can explain that mathematically. So as we introduce more slits into the equation, d, which is the distance between them, is going to go down. But notice that n, the change in n, it's fixed at 0. That's going to be constant. And the wavelength is also going to be constant. The green light is green light is green light. It's going to, by definition, it's going to have that wavelength. So this is set. So if D goes down, the only way that this equation can still hold is if sine theta goes up. And the only way that that can go up is if theta goes up. So if we have our grating slit, and here is the primary line, this angle here, the theta angle here, is going to increase as we have more slits. It's that sort of paradox. You would think that as they're getting closer and closer and closer together, we would have more and more and more bands, but in fact we don't. We have the opposite effect. And it's a quantum physics phenomenon. I'm not going to get into the physics right now, but you just need to know this relationship. So I would go straight to this equation. If you don't have this equation, you're going to be kind of fumbling around explaining things. But if you know what these mean, so this is the distance between the gratings, this is the distance, this is the number of bands, and this is the wavelength of the laser. Okay, last question. In another experiment, so different set of circumstances, also with a grating, also with a green laser. The green laser with a wavelength of 515 nanometers, so I guess the same laser as we had in the first part of the question, is shone through a different diffraction grating, and 7 maxima are seen on the screen. The screen is 0.9 meters wide and is 1.2 meters from the diffraction grating. Calculate the possible range of values for the slit separation of the diffraction grating. Okay, so let's sort of unpack this. So there's going to be 7 bright spots. So remember these, there's going to be a bright spot here, 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 and here. So this is going to be bright spot 0, 1, 2, 3. And this is going to be 1, 2, 3. Because remember, it's not sequential, it's the distance from the central point here. Alright, so if we want to know the possible values, we're going to have it so that the screen, let's actually go to the top so it's positive numbers. So it's greater than this distance here, but not greater than this distance here. So it's going to be a sort of what would be the bandwidth so that we get the third but not the fourth. So there isn't a sort of fourth one up here that would be possible. Okay, so how are we going to do it? Well, we're just going to go straight to the formula that we just used. So if you remember, the formula is D sine of theta, I'll even do it in green, is n lambda. So let's look at what we've got. We know the n that we're looking for. Well, we're looking for 2 distances, aren't we? So let's set this to 3 so that we find this distance from here to here. So this is going to be 0.45 meters because this is 0.9, so half of that is 0.45. Then let's do the same for 4. So if we have 4, we can have that, but we can't have that. So we find the range. Okay. So I'm going to let n equal 3, and we know that lambda is 515 nanometers. So 515 times 10 to the negative 9 meters. And the distance here is 0.45. So that's not the distance that we want. So this is 0.45, but that's going to be okay because we're going to need to work this out. In order to find D, we have to find theta first. Okay, we're looking for that in order to find this. So how are we going to do it? Well, we're going to do it by trig. So if we ignore everything except for this line here, this line here, and this line here. So we have a right angle triangle. And we know what these sides are. So this is going to be 0.45 meters. And it tells us that this is 1.2 meters. So we want to know what this theta 3 would be. So we've got opposite and adjacent, so we're going to use tan. So theta 3 is going to be tan inverse opposite 0.45 over 1.2, opposite over adjacent. And we put that in our calculator, making sure that we're, I guess it doesn't actually matter if we do have it in degrees, but let's stick to radians. So 10 negative 1, 0.45 divided by 1.2, close brackets. So 0.3588. Let's go 4 decimal places. Radians, just to show that it's radians, not degrees. Okay, now we've got what theta is. Now we can find what D would be. Can't we? So D times 0.35, jump ahead of myself, it's going to be sine of that, isn't it? Times sine of 0.3588 is going to be equal to n, which is 3, times the wavelength, 515, times 10 to the negative 9, and we want to solve for D. So D, the minimum distance must be 3 times 515 times 10 to the minus 9 divided by sine of 0.3588. And all of the dimensions are going to collapse and we're going to get something in meters. So let's do the top. 3 times 515 times 10 to the negative 9 divided by sine of 0.3588, bracket. So 4.3999 times 10 to the negative 6. So 4.3999 times 10 to the negative 6 meters. So that's the minimum distance between these slits. And now we do exactly the same thing. So that's our minimum value. So now we have to do the same thing over and over again. So now n is going to equal 4. Was there? The lambda is going to be the same, isn't it? That's going to be the same there. Now we need to find out what sine of that theta is. So now we don't know what that is. What is this theta going to be? So theta 4. How are we going to find that? And the answer is that we can't really do it because we have one equation and two unknowns. So we can only do an inequation. So we know that theta 4 must be greater than 0.3588 radians. So if we know that as D goes down, the gap increases, so that means that D must be less than 4, which is n, times the wavelength, 515 times 10 to the negative 9, over sine of this number, isn't it? So it's going to give us a maximum. So in other words, n equals 4 is there, and n equals 3 is there. So this point here has to be somewhere between them. And we know what n equals 3 would need to be, the maximum, and now we need to work out what this is going to be. Okay, yeah. So this is going to work. So we're going to grab our calculator at this stage, aren't we? So 4 times 515 times 10 to the power of negative 9 divided by sine of 0.3588, brackets, and our final answer is 5.866. 4 times 10 to the negative 6, and it's the same scale, so we're good. So therefore D must be less than 5.866. 4 times 10 to the negative 6 meters. So that tells us that D is in the middle here, so it's got to be greater than or equal to 4 point, what did we say it was? 4.3999 times 10 to the 6. And I know I'm using too many digits here, but it's the last question. And 5.866. Too many sixes, 4 times 10 to the negative 6 meters. So 1, 2, 3, 4 decimal places. 1, 2, 3, 4. Okay, well, same number of decimal places. And that is our final answer. And that is the exam. It was quite a challenging exam, actually. It's quite a bit tougher than the mechanics exam, especially the last question. If you didn't know the slits and the greats questions, what the equations meant, you'd be lost. My advice is to go through those equations. The only equation that you really need to know is the length of the harmonics. So it's the length of the harmonic is going to be 2L divided by N, and then frequency 1, length 1 is going to be equal to frequency 2, length 2, as long as the same string for the standing waves. So those two equations there, it would behoove you to know what they mean as well. They're not given to you. You can kind of work them out, but a lot quicker if you know what they are and how to use them. For the waves, the equations, always go back to the equations. And that's the end of this exam.
You know, I have